Okay, welcome to lecture 12. So we start talking about a line decoder, which is a dual line decoder. So 2 to 4 line decoders, but we use 2 line decoders together, like in this figure here. All right. So this is 2 to 4 line decoder, and this is 2 to 4 line decoders in the same chip. Here are the two inputs of the first line decoder, the selection inputs, and here are the two inputs for the second line decoder, the selection inputs. And this is the truth table showing the operation of this dual 2 to 4 line decoder. If it is enabled, he is 0. All right. The 0 select inputs makes y o bar 0, 0 1 makes y1 0, 1 0 makes y2, 1 1 makes y3, the usual way of operating the line decoder. All right, good. We talked about the NAND gate as a decoder, the 3 to 8 line decoder, the integrated circuit chip, and recently they have a decoder that could be programmed. They named it PLD, Programmable Logic Device Decoder. So you will use a logic device to be programmed according to users' need and system needs. So you can use a PLD and program it, and of course reprogram it the way you wish. Okay. And we have three forms of programmable logic devices. The PLA, Programmable Logic Array, it's a logic elements in an array that can be programmed. So you distribute logic gates in an array in a way you can easily program it, and programmable array logic and gate array logic. So these are three different forms the PLD can take, any one of these three forms. Okay, and most of the modern microprocessor based systems and memory interfacing systems we use PLDs, PAL instead of PROM, PAL and PLAs, PALs and PLAs, they are fuse programmed. So they have connections that are fused. A fuse connecting 2 points, you leave it if you need to program it with a 0 or a 1. You burn it out if you need the inversion of a 0 or a 1. All right. So these are only programmed once, because once a fuse is burned, cannot be put back. And there are some of these PLAs where you can erase the program and reprogram it like the EEPROM. Okay, the most famous PLD used is the 16L8. This is commonly used in interfacing memory with processors or in decoding addresses. And it is first used with the 386DX processors, in particular when decoding 32 address, 32-bit address. So now we have 32 bits, 32 lines connected to a memory. This 32 lines or 32 bits is much larger than the address bits or lines in the memory. This is why we need to decode this 32-bit address. Okay, this 16L8, the PLD, has 10 fixed inputs. 10 pins of the PLD 16L8 are used for fixed inputs. These are pins 1 through 9 in addition to pin 11, and 2 fixed outputs, pins 12 and 19. So pin 12 and pin 19 are used for outputs, fixed outputs. So they cannot be used as inputs. You cannot use them to bring in data to this PLD. They are only used to get data out of your PLD. In addition, we have 6 pins that are used as inputs or outputs at users' wishes. If you wish to use them as inputs, you can. As outputs, you can. These are pins 13 through 18. Good. Let's see an example of using a PLD. Here you are. This is the 16L8. Okay. These blue pins are used for inputs only. Okay. These 6 pins are used as input or output. 12 and 19 used for output only. All right. So we need to decode address pins A19 through A13 coming from the microprocessor, all right, going to the memory, all right, and we need to decode these to 8 outputs. So you have a microprocessor which is connected to maybe one, two, three, up to 8 different memory chips, and we need to select one of these 8 one at a time. How do we do so? We're going to use the output pins 01 through 08 to select one of these 8 chips. Okay, so we need a low signal to go through a line connected to the first chip. Another low signal goes to the second chip if we need to access any memory access in this, and so on. A third low signal that goes to the third memory chip, and so on. So we need to connect 8 different memory chips through this 16L8 to enable it to get communicated with your microprocessor. Okay, we do this by programming. So we make O1 low, this is bar, when these are the pins of your microprocessor to be decoded to select one of these 8 memory chips. So we produce at O1 a low signal whenever A19, A18, A17, A16 are all ones, while 15, 14, and 13 are low. Here is the bar. And we do the same with O2 is low Whenever these are high, these are always high, okay? And we assigned the least significant 3 bits of the given range to select among the different 8 chips. This is, let's say, for the 0 chip. This is for the first, for the second, for the third, and for the 7th chip. So these signals become low. For example, the first one, when these are all zeros, then 1, 0, 0. All right, this is for the first chip, okay, or the chip enumerated 1, which is the second chip. Here is, okay, for example, this is 0, 0, 1 for the fourth, for the fifth chip, enumerated number 4, if we start enumeration from 0 to 7. Okay. Regarding the 8088 series, 8088 and 188, where the address bus is a 20-bit address bus and the data bus is 8. Okay, so the memory sees these processors, especially 8088, as such. They get communicated with the processor through 20-bit address connections, 8 data bus, 8-bit data bus, and 3 bits as a control signal. 3 bits as control signals, one for memory, read, and write. So this is from the point of view of memory. We communicate with the processor through address bus, data bus, and control bus. Okay. So now we need to design a system which uses the microprocessor 8088 and connected to 32 kbytes of EEPROM using this specific range of addresses. Okay, and we use as well this specific memory chip. This specific memory chip is an EEPROM, a 27 series. The total number of bits inside this memory chip is 32K bits, organized as such, 4K memory locations, each of 8 bits. So the chip is composed of only 4K bytes. We need to interface 32K bytes of memory using chips each of 4K bytes. So we're going to use 8 of such a chip. So this is the first problem. The second problem, we need to connect 512K bytes of static RAM using this address range to the same 8088 microprocessors. Again, using this specific series of static RAM 62, composing of a total of 256 bits, organized as such, 32K memory locations, each of 8 bits. And we need to connect a 512K bytes using 32K bytes chips. So we'll need 16 chips to be connected to the processor. So the first example, we need 8 memory chips to be connected, 8 EEPROMs to be connected, 8 EEPROM chips to be connected, and here we need to connect to our processor 16 SRAM chips. How do we do so? We'll see. Let's first talk about the EEPROMs, not the static RAM. So we need to connect 8 different chips to your microprocessor. Good. 8 different chips. And remember, the microprocessor provides you with a 20-bit address, while each of these chips is only 4K, which means they can be accessed through only 12 pins. 2 to the 12 is 4K. All right. So again, you have a 20 pin connections or a 20-bit address that has to be decoded to 12 pins. So definitely we'll need here a decoder. To do what? To decode the 20-bit address into 12 pins or 12 bits only, in addition to choose among different memory chips. We'll have 8 different memory chips. We need a decoder to decode a larger number of pins into smaller ones, in addition to select among different memory chips. All right. So this is each memory chip is 4K by 8, and we have 8 of them. This is why we're going to use 3 to 8 line decoder. So we're going to use 3 of these extra 8 bits. We're going to use 3 of them to select among these 8 different chips. Okay, good. In addition, the EEPROM of series 27 is a sort of a slower memory device. This is why we need an insertion of a wait state to let the processor slow down a bit for it to access correctly memory locations within the 2732 chip or EEPROM chip. Okay. This is because the EEPROM has access time of 450 nanoseconds, in addition 12 nanoseconds for the decode to decode an address, for the decoder to decode an address, so making altogether be of 462 nanoseconds. So the memory with the decoder requires 462 nanoseconds. Okay, while your processor, as we previously mentioned, allow the memory to get access to provide data or take data in 460 nanoseconds only. So this takes longer, which requires a wait state. Okay, because 8088 at 5 megahertz allow only 460 nanoseconds. If you need more than 460, you have to generate a wait state to let the processor slow down a bit to access your memory. Good. So a wait state will add a single clock cycle of 200 nanoseconds to the 460, making them 660 nanoseconds, more than enough for your memory to get accessed. Good. And here is the final system. All right. First, your A0 to A11, 12 address bits are brought through your address bus to each of these chip. So we're consuming now 12 bits of your address. How about the other 8? The other 8 are used as such. From A19 to A15, remember here, this is the range, this is the required range of addresses, which tells you that the 4 most significant bit as well as the next most should all be ones, because you have here 8 and you have here F. So these 5 most significant bits should always be ones. 5, 1, 2, 3, 4, and 5. So we're making the 5 most significant bits of your address, make all of them 1, and provide them to the NAND gate. Okay? Why are we doing so? Because you have here 5 ones, and they will always be kept ones. We'll never need any of these 5 bits to be 0. In addition, we're talking to a memory, so IO/M is low. Through this inverter, it becomes high. And this high voltage is connected to the rest of your NAND gate inputs. And they are all ones. So the NAND gates get this gate is an 8 input NAND gate. 5 inputs are made ones from your address most significant 5 bits, and a sixth input of your NAND gate is made 1 through this signal, and we have additional 2 ones coming from this source. So now they are all used to decode a single low bit used to activate this decoder. So they provide zeros for your G2A and G2B. Okay, while this 5 source is providing a high voltage to G1. So now we make sure that your line decoder is active. Then we're using these 3 address bits, A14, A13, A12, to select among these 8 outputs, to make one of these outputs low at a time, only one low at a time, when communicating with one of these 8 memory chips. So for example, if A12, A13, A14 are all made zeros, which means what? You have now 1, 2, 3, 4 ones, and then your A15 is always 1. Okay, you have 4 ones from this F, and this one from the 8, and you make the rest zeros. 0, 0, 0. Okay, and 3 hexadecimal zeros. Each is composed of 4 binary zeros. So this is your beginning address. When you make these zeros, you activate this 0 line, which select this chip. The beginning address of this chip is when you make A11 through A0 all zeros, which means what? your beginning address as needed is F8, then 0, 0, 0. And your end address is when these are made hexadecimal ones, which means F, 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 which is the ending address of your chips. Okay, so your address space now is correct from F8000 to FFFF. Okay, when it comes to this chip, your beginning address is equal to F8000. You add 4K to it to get this ending address. So this is the range of addresses of the first page or the first memory chip. And you can do the same for the second page, the third, and so on. Okay, and here you are. These are your first ones, A19 through A19, A19, A18, A17, 16, and 15. A19 through A15 are all and always made ones. Then the rest could be ones and zeros depending on which memory chip you are communicating with and what memory locations you are trying to read or write. So if they are all made zeros, this would be the overall beginning address of your 8 chips. If they are all made ones, this will be the ending address of your memory system, the last address in your last memory chip, in your 8th memory chip. Regarding pages, the first page is when you make all zeros, all right, which gives you this address, and the last, you're still in the first page, so you have to keep these 3 zeros. Okay, you're selecting the first page, then these 3 zeros should be kept, and you make the rest ones. So this is the ending address of your first page. So the address range of your first page is from F8 3 hexadecimal zeros to F8 3 hexadecimal Fs. And you can go ahead, if the beginning address of your next page is, you add 1 to here. If you add 1 to here, this 8 would be 9. And this is your beginning address of your second page. This is the beginning address of your second page. Okay, so when you add 1, you make 0, 0, 0, and 9, F. Okay, good. To this, and you can go ahead and determine the address range of each one of your 8 pages. This is it for the EEPROM. Now comes the static RAM. We need to connect 16 different chips to your 8088 processor. All right, 16 different chips, because each chip is composed of 32K only, and we need to connect 512K bytes. So we need 16 of such a chip. Each chip is composed of 32K bytes, and it is required to interface up to 212K static RAM. 212K static RAMs, each of 32K, so you require 16 different chips. So we'll have 16 pages. Okay. The access time of your memory static RAM is in the order of 10 nanoseconds. So we don't need any wait states. And here is your system. How many decoders do we need? We need 3 decoders. One decoder to select among 8 different chips. Okay, let's say the highest addresses of your system, and another decoder to select among the lower 8 different chips. Okay, and we need an additional decoder to select one of your decoder, the upper one or the lower one. So because we have upper 8 chips, we use a decoder to decode one of them. Lower 80 chips, we use another decoder to decode one of them. And to select the upper or the lower, a third decoder is needed to select between these two different decoders. Good. And before we provide your address bits, you buffer them. Okay, you buffer them. For example, here each page, each memory chip, which is composed of 32 kbytes, requires 15 address pins from A0 through A14. So we'll take from A0 to A14, but we buffer these 8, so we need 15 different pins. 8 of them are buffered through this buffer, and the other 7 are buffered as well in the other buffer, and they are provided through these buffers to your memory chip. So these are the 15 required pins connected to each of your page or each of your memory chip. Good. How about the rest? All right, we're given some address range. Looking backward to the address range given, you would see that, okay, E15, E16, A16 and A17 are now used to select one of memory locations, either upward or downward. They are never activated at the same time. So for example, if you need to access the first address in this first page, okay, so you provide here 0, 0, 0. They go through here, upward or downward. But if you need to access this, you will have to activate only the upper decoder. So when the upper decoder is active, these 3 zeros go to here, making this 0 line low, activating this page. If you provide A0 through A14 all zeros, you access this memory location. Okay, good. So again, we have to interface 16 different chips to our system. We arrange these 16 into 2 8s, upper 8 and lower 8. We use 2 decoders to access any of these upper or lower 8s. Each group, upper or lower, requires a 3 to 8 decoder. Because we have 2 decoders, we have to use a third decoder that selects among the upper decoder, or selects between the upper decoder and the lower decoder. And we see that all address bits before used are buffered. Good. Okay, so you can follow the connection of this system easily. Okay, for example, A18, A19 are used to select the upper or the lower decoder. You may assign 00 for this line to be low that goes and activates the upper decoder, and 10 makes this line to be low, which goes and activate the lower decoder. I guess you can easily now follow the given connections and make sure that the design is made as required, connecting 512 kilobytes of static RAM to your system through 16 different chips, each of 32 KB. Good. Again, this is 512, 32 times 16. Okay. This is your address range from 20 zeros to 19 ones. We have F, 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 F. 4 by 4 is 16, and this 7 gives you 3 additional ones, so 19 ones. The first 3 by 8 decoder selects upper or lower decoders. When you go to upper or lower decoders, you use these 2 bits, 00 for the upper, 01 for the lower, and these are used to select the different addresses depending on which one is active. If this is active, they are used to get access to a memory location from any 8 different chips connected to your system, but the upper ones. And if the lower decoder is activated through 01, these same pins are used to access any memory location from your lower 8 chips. And again, this is a complete system where your data, as well as the control lines and address lines, address, data, and the control, they are all buffered. Buffering these bits, okay, allow the system to do whatever it's supposed to do safely. You let the address stay in the buffer for a while, as well as the data and the control address and the control pins, till the operation is completed safely, read or write. Okay, now going to the 8086 series. They are different from the 8088 series in the way the data bus is composed of. Your data bus here is composed of 16 bits and not 8 bits. So these machines are different from the 8088 in this. The data bus is 16-bit. Again here, the IO/M bar used in 8088 is reversed for the 8086, 1886, M/IO bar instead of IO bar/M bar. And in higher versions, 286, 386, they use different signals. They call it memory write control and memory read control in 286 and 386. Okay. Now, your memory is divided into 2 banks, high bank and low bank. Low bank starts from 0 and goes by even steps, 0 to 4, and the high bank starts from 1 and again goes 1, 3, 5, 7. So you have additional pin in the processor named bus high enabled. You have to provide a zero signal to this pin whenever you need to access a memory location from your high bank of your memory. While your bus low enable, if you need to get access to a memory location from your lower bank, you have to activate this pin BLE bar. You have to provide a zero to this pin of your microprocessor, and we do this by dedicating the least significant bit of your address, which is A0, to activate the lower bank. So the lower bank is activated separately and independently by A0. Good. Again, we mentioned this before. The 16-bit data bus presents a new situation to your microprocessor, because then you will have to divide your memory into two banks. You have 16 bits, you have to have two banks. Why two banks? Because you can deal with 8-bit or 16-bit. Okay? So in a memory, in a clock cycle, you can get 8 bits out of your either the even or the odd bank, or at a clock cycle you can at the same time get 16 bits, 8 from your low bank and 8 from your high bank. So you do so to make use of your wider data bus of 16 bits, so you can get out 16 bits or bring in 16 bits at a time at a clock cycle, while you do this in 2 clock cycles if your data bus is only 8 bit. All right. Okay, so now in these 86 series, where your data bus is composed of 16 bits, you would have to divide your memory into two banks. Okay, a low bank, low because the beginning address is 0, and a high bank, high because your beginning address is 1. And you go through odd addressed memory locations, 1, 3, 5, and so on. Here you go through even addressed memory locations, 0, 2, 4, and so on. And your high bank deals with D8 through D15 of your data bus, and you select this high bank by activating this pin BHE bar, and your low bank deals with D0 to D7 of your data bus, and you selected this low bank by making BLE active or sending a 0 signal to this. And again, we send a signal to activate this low bank through A0, the least significant address bit. Okay. So BHE and BLE are used together to select one of these two banks or both banks at a time. So if they are made 0, 0, both banks are enabled, and you can get into the memory or take out of the memory 16 bits at a time. If you activate the high bank only, you get 8 bits from the high bank. If you activate the low bank only, you get 8 bits only from your low bank. If you don't activate any of them, you don't deal with the memory, you're not communicating with the memory, and no bank is selected. Good. Again, bank selection can be accomplished in two different ways. You can use separate decoders to each bank. All right. So as we did in our memory example of static RAM, when we made separate decoder for each of the 80 chips, here as well, you can get separate decoder to decode signals to activate either one of the two banks through chip select. Okay, or you can design a system to generate a strong signal to each bank, which drive the read. Okay, but again, you use A0 to activate the B bus low enable pin. So A0 is never connected to the memory. Dealing with the 86 series, you don't use A0 as the least significant address bit. You start connecting your memory from A1. So A1 of your bus is connected to A0 if your memory, A2 if your bus is connected to A1 of your memory, because A0 is reserved for activating the low bank of memory. Okay. If you use separate decoders for your low bank and high bank, this is your address, which is what? Which is A1 through A16. So we're using 16 bits of our 20-bit address. Why are we using 16? Because each chip is composed of 64K bytes. So 64K bytes requires 16-bit to access, requires 16 bits to access each of these memory locations. This is why we are sending 16 bits as an address. Okay. These 16 bits can go to either your high bank D8 through D15 or low bank D0 to D7. Okay, enabling you to access any memory location depending on your choice from the high bank or from the low bank. Good. Okay, now we're using a microprocessor which has 24, not 20, 24 address bits. Okay, so you're sending A1 through A16. How about A0? Where is A0 here? A0 here is used to enable the lower bank of your signal. okay, your BLE, okay, bus low enable, gets its signal through A0. Okay, good. Now, if you are to access a memory location from your lower bank, D0 to D7, you have to activate this decoder. How? A0 is made low and connects to BLE to make G to A low, and this third decoder is activating this lower decoder, and if you are reading from your memory, you have to provide this memory read control strobe. Okay, if now you're sending 3 zeros, okay, they come to here because this is now active. Okay, while your bus high enable could be active or inactive. Let's consider now it's inactive. The signal sent to this is 1, and we are dealing only with the lower bank of your memory. So these 3 zeros will come here. This is now is not active. This decoder is not active because BHE is high, making these 3 zeros go down and start accessing memory locations inside your lower bank. If the opposite is the case, which means A0 is made high, while BHE is made low, meaning you are activating this decoder and deactivating the lower one, you can access any memory location from your high bank. Okay, and the third situation is when you make your BLE and your BHE are both high, you activate both decoder and you get a byte from your high bank and another byte from your low bank. These 2 bytes bring to the data bus 16 bits, 8 from the lower bank and another 8 from the higher bank. Okay, so this is the way the memory is arranged and is read from and written into through your 86 series of Intel's processors. Good. Again, these are 486 memory interface. Here, your data bus has evolved to 32 bits, which means what? Meaning you can read or write 32 bits at a time. Again, memory chips are byte addressable. So to get at a closed cycle 32 bits out of your memory, you have to arrange your memory into 4 different banks. Each memory location is a byte. Okay, so at a clock edge you will get 4 8-bits, 4 bytes from each of these 4 banks, so you can get 32 bits at a time. You can never be able to do this unless you divide your memory into 4 different banks, because you have a data bus that can be filled out with 32 bits at a time. Okay, so you can bring in 32 bits at a time or even send out 32 bits at a time from your data bus. You will never be able to do this unless you divide your memory into 4 different banks. When you divide the memory into 4 different banks, you can bring in 8 bits, 16 bits, or even 32 bits. Good. So you have to arrange your memory into 4 different banks. And doing so, you can bring in or send out 32 bits at a time, 16 bits at a time, or 8 bits at a time. Now we have 4 banks, so we have to have 4 different signals to activate each of these banks. We call bank 0, we activate it by BE0, bus enable 0, BE1 to activate the first bank, BE2 to activate the second, BE3 to activate the third. So we have the 0 banks, the first, the second, and the third. So we have to assign 2 bits of your address to deal with these 4 different banks. This is why now your A0 and A1 of your address bus are used and dedicated to be used to select among these different 4 banks. So again, when you connect a memory device to your 386 or 486 microprocessor, you start connecting from A2 of your processor to A0 of your memory, A3 to A1, and so on. So you never use your A0 and A1 of your address bits of your microprocessor. Okay. Good. Of course, this makes a higher rate of operation of data transfer of your microprocessor. So you can increase the speed of your processor by either increasing the clock, make your processor operate at a higher clock frequency, or you widen your data bus. Make your data bus in a clock cycle carry more bits. How about the Pentium? The Pentium memory interface. So how to interface Pentium Pro or 2 or Pentium 3. Here your data bus has further evolved to 64 bits, which means what? Which means in dealing with interfacing memory with your Pentium processors, you have to divide your memory into 8 different banks, because your data bus now is composed of 64 bits. You have to group them into bytes, 8 bits, so you have to make your memory divided into 8 different banks. So we have to have 8 different decoders to activate one of these 8 different banks, or 8 different write strobes. Strong signals for write. We use 8 different of them, and we send one if we need to activate a single bank, 2 if you need to activate 2 banks, or you send all 8 strobes if you need to activate the 8 banks at a time to read or write 64 bits at a time. All right, so now you need what? You need 8 different bus enabled signals. So X from 0 to 7. This is why now you use A0, A1, and A2 of your address bus. So you start connecting A3 to A0 of your memory, A4 to A1 of your memory, and so on. Because the first three, the least three significant bits, are used and dedicated to select one of your 8 banks in, of course, interfacing memory to your Pentium processors. Okay, and you use these, all right, to generate strobes, a memory write control strobe or a memory read control. Okay, here we are going to show how the write strobes for Pentium 4 are generated. So the write signal, the high write signal coming from the microprocessor, and we're talking to a memory. So the signal M/IO bar is also high. So we have the two inputs of this NAND gate are 1s, producing a low signal to activate the write cycle of your system. This is write microprocessor write control. This is memory write control. Memory write control. This memory is fed to all 8 OR gates, which are used to generate the write strobes for each of the 8 different banks connected to the Pentium processor. So each of these OR gates receive a low signal coming from this NAND gate. Okay, if another low signal is brought in by your processor for BE0 to be active, so you received a 0 here, okay, and a 0 was already there here, while the rest of your bus enable inputs, let's say, are inactive, they are all 1s. So this is the only 0 here, the write strobe of the 0 bank. So in this case, you are trying to write 8 bits into the 0 bank, and this is the only bank which is active, so you write your 8 bits. On the other hand, if you received 2 bus enabled signals active, 2 zeros in here, BE0 and BE1 are both zeros, these 2 OR gates will produce 2 zeros, which activates along with this 0 bank, the bank number 1, enabling the system to write 16 bits at a time. Okay, similarly, if you activate all 8 write strobes at a time, all 8 pages, all 8 memory chips will be active at a time, enabling you to write 64 bits at a time. Okay, this is how write strobes are generated. Do we need read strobes to be generated as well? No, we don't. We need only a single read strobe, because using this single read strobe will open up all 8 memory chips, all 8 pages will be opened up, and 64 bits will be loaded to your data bus, and you pick whatever bits you are interested in. You can pick 8 bits, 16 bits, 32 bits, or all 64 bits. So in reading, you don't need to work with each page at a time, to open up only a single page at a time. While when you are writing, you need to specifically determine which memory location you are going to change the data in. In reading, we don't change data. So if all data are available, you pick whatever portion of your data you're interested in. So you don't need to generate read strobes. Okay. Here is the circuitry which shows you how these 8 memory chips, 8 memory banks are connected to your Pentium processor. We have 4 upper banks and 4 lower banks. And we're using here the PLD, the programmable logic devices 16L8, to enable your banks. For example, here, as we said previously, we have 8 banks, so we dedicate the 3 bus bits A0, A1, and A2 to select one of these 8 banks, while the memory, we connect A0 of your memory chip, of your memory bank, to A3 of your address bus, A2, A1 to A4, A2 to A5, A15 to A18. Okay? And your bank is composed of 64 bytes. Okay? So it requires 16 bits. So this is why we're connecting A3 through A18 to each of your banks through A0 through A15. Okay, good. All right, the rest of your address bits in this Pentium, we have 32 address bits from 0 to 2 for selecting a bank, from 3 to 18 to select a memory location, from 19 through 31 to enable all 8 banks, to select all 8 banks, and specific banks will be dealt with depending on your write strobe. For example, this low signal is taken to feed the chip select inputs of your banks. So all banks are selected. All right, good. And if your write 0 strobe is the only signal which is low compared to the other write strobes, so your WR0 is low, so you're trying to write data 8 bits at a time to this 0 bank. If your write 1 strobe is active along with your write 0 strobe, you're trying now to write 16 bits from your data bus D0 to D7 goes to bank number 0, while, because this is now active, D8 to D15 goes to your bank number 1. If all write strobes are active at a time, okay, so you're writing 64 bits at a time, you're taking D0 to D7 from your data bus, write them into your 0 bank, D8 to D15 into your first bank, D15 to D23 into your second bank, and so on till you write your D56 through D63 into your 8th bank. Okay, while if you are trying to read a data, you need only a single memory write control, which goes to all chip select, to all 8 banks. So all 8 banks will be opened up for you, and all 64 bits will be loaded to your data bus. If you are interested only in the least significant 8 bits, you take them from bank number 0. The least 16, you take them from bank number 0 and bank number 1, and so on. Here is the wiring of connecting or interfacing the Pentium 4 with 8 different banks. These are the two PLDs, programmable logic devices, which are used to select a low signal that goes to the chip select of each of these 8 banks. Here is the address A3 through A18. This address goes to each and every bank. Okay, good. And this is your data bus. D0 to D7 goes to this bank, the first bank or the bank number 0, and D8 to D15 goes to the second bank, third bank, fourth bank, and so on, fifth, sixth, seventh, and eighth bank. So this is actual wiring of the Pentium 4 when interfaced with 8 different memory chips composing the 8 different banks you deal with in programming the Pentium 4 processor. Okay, now we are going to use two PLDs, 16L8, to interface our memory to your Pentium using this address range. If you look closely to this address range, you have 4, 8, 12, and the most significant one of these 8. So we have 13 address pins, the most significant 13 address pins that have to be always high. This is what we are going to decode them to produce what? To produce the chip enabled signal. So whenever these are all ones, a low signal is produced at this pin. We name it U2. So U2 is low as long as your A19 through A26, 28 are all ones required by this address range. In addition, A29, A30, and A31 are also high. And with this signal low, and we send 3 ones here, we activate this pin 08. Activated means we send a low signal to this pin. This low signals, we named it chip enable, which is low whenever U2 is low, A29 high, A30 high, A31 high, and we use this signal to enable all memory chips. Okay, and this is the end of our course because of our current situation. May Allah have it go away soon and we come back to our regular life. So we meet now at the final whenever it is decided by the administration, whether it is a term paper or an electronic exam, an online exam. And whenever this is decided, I'll let you know. Thank you.